Hello. So let's look at our first calculation of complexity, number 3 I assigned. I'm going to only do these two. I also assigned you two complexities from algorithms that I described in the previous video. I hope you look at them and figure it out. But let's look at these two. So the algorithm here that we have is, I'm just going to copy it from the book. So this is a certain procedure. For some reason they don't say what the procedure is. So I'm going to say procedure. It doesn't have a name, so I'm not going to name it. It should have. It involves a list, so I'm going to do procedure 3. I'm going to call it just 3 because it's the third one in the book. Okay, and it has this, and the ANs are what? Positive real numbers. You're positive, but I don't think that matters. Okay, so we put m equal to 0, then we have a for loop for 2, and it is for I going from 1 to n, and then this is inside that is another loop, so we know what this kind of things could mean. And this is for j going from I plus 1 to n. And then in there we have to do the maximum of, we calculate the maximum of the product AI, AJ, and M. There might be a strange that we use M both in, again, we have seen this many times, right? So we can have M here and M here. Now think of what does this do? Well, it's going to replace this M by a new value if this AI times AJ is bigger. So in the beginning everything is 0, but eventually this M will get bigger and bigger, and each time we have a product of two of these elements that is bigger than what we have, that will be the new value. So if you think about it, what this will give at the end is the M will, so okay, yeah, we should say this here, right? Return M, and then what is the solution? So between commentary, M will be the biggest product of two numbers. So of all, we have this list of real numbers, and the biggest product that will be also okay. So let's make them positive, so we don't have to deal with negative numbers. That's what it said anyway in the book. But that's not really the question. The question is not what does it do, but the question is what's the complexity of this thing. Okay, so let's analyze this. Well, this first one will only be carried out once, so that will add to a 1, but we kind of know that we don't really need to look at that. Well, instead, because it will never, it's too small to contribute to the complexity. Okay, we have a loop, but we shouldn't go just there. We have to go inside the loop. We should not stop there. We have to go inside until we can no longer inside. So the most inner one is this one, and the complexity of this is, well, you could argue here a little bit. We have to do a product, and we have to do a calculation of a maximum, and we have to do an assignment. So you could call this 2 or 3. I'm gonna say 2. And why can I be cavalier about that? Can I be relaxed about that? Is because it's a constant, and these constants, they will never matter. Okay. Now, how many times? So now is and this is a harder problem. How many times is this guy? Oh, this is not what I want to do. This in this color. And how many times is this carried out? And we see something that we have not seen before, is that this depends actually on I. So we are inside the loop, and I has a certain value, but we see that the bigger I gets, the less I have to work here. In fact, if I is equal to n, then this j becomes n plus 1, and when we have a loop where the counter is higher than the bound, then it doesn't do anything, right? So, but that's just a technicality. But anyways, the number of times it does is always going to be less and less. Well, let's write down how many times it does it. Well, I plus 1, I plus 2, all the way to n. And if you think a little bit about it, that is I n minus I times. So I'll write it here. Let me get rid of this line here. So n minus I times. N minus I times we do this. Okay? If you don't believe me, we'll take I equals 0, then we go from 1 to n, that would be n times, and then n minus 0 is exactly n. And again, if we were off by 1 here, again, it doesn't really matter. So how does this affect now the rest? Okay, so we know now how much the inner loop is done. Now we have to think about the outer loop. How many times does we have to carry this one out? Now it's a loop that just loops from 1 to n, so we're gonna n times. Oh, okay, sorry. I forgot one stop, right? I said this loop will be carried out n minus I times, but each time it does 2 basic steps, so I had to multiply here with 2, so it's 2 times n minus I. Sorry, I forgot that part here, but it's not irrelevant, right? But just to be complete. Okay, so now how many times will we carry out this loop? Well, it's just simple n times. So we're gonna have this whole thing will be n times this. We have to do that. So 2n n minus I. Yes, but that is a little bit of a problem here. I cannot formulate it that because I don't know what I is here. So I have to reconsider a little bit my calculation here. I say, okay, it is carried out n times. What I should say is this: as I goes from 1 to n, each time I will do this many steps. So I'm now really writing it out. Before we say, okay, if you have a loop, from 1 to n, and you do three things in that loop, then how many times are you gonna? How many steps is the whole when the loop is finished? Well, 3 plus 3 plus 3 plus 3 n times, right? Okay, and therefore we say 3 n times because they're all the number of steps is always the same. But since the number of steps changes here, I should be more careful, and I should say, okay, how many basic steps do I carry out? Well, if I is 1, then it will be 2 times n minus 1. If it's I is 2, then it will be 2 times n minus 2. And so on. And so I have to add all these numbers up. So what I'm adding up, what I'm looking for is actually this number, this sum number here. So let me come down here. So it is summation 2n minus I, for I going from 1 to n, plus 1 actually. Don't forget we had this little 1 here upstairs. So this is the total amount of steps. Now this is perhaps less clear what this is, so we should work it out. Now we have tables, remember, so let's see what we get here if we expand this a little bit. So there's a summation I going from n1 to n, 2n, minus 2I plus 1. Now I'm going to split this summation in 2 parts. I'm going to summate the sum for I going from 1 to 2n minus the sum I going from 1 to n to I plus 1. Is that allowed? Yes, of course. You can, if you take the sum of this minus this, then you can take the sum of all these, take the sum of all these and subtract. Sum goes, that you can, what it means is basically rearranging the terms in a summation. Now, what is this? Well, we do n times, we take the same number. Wow, that's just multiplication, right? This is just 2n squared. Now, what is this? Well, let's bring the 2 out. It's twice that sum. Okay, I'm going to keep calculating 2n squared. Now this one we had in a table. Somewhere there was a table that tells us how many times it is, and actually if you look at the table, it's n times n minus 1 times n plus 1 divided by 2. Oh, that's nice because the n's cancel now, plus 1. So what do we have now? We have 2n squared and then minus n squared minus n plus 1, right? Because this minus n squared and this minus n. So we get n squared minus n plus 1. Now, the whole big O of this is just n squared. The lower terms don't matter. So what this looks like, it seemingly look like we are doing less here, because as we have to do, if I increases, as we go more and more inside the I loop, the less the less long the J loops will be, and the hope would have been that this cuts down the whole calculation, but it doesn't, right? So if I would have here looped from J from I plus 1 to n, or from J from 1 to n, it would not have changed the complexity of the algorithm. It would have done more steps, but the complexity would be still the same, namely n squared. Okay, so this is perhaps, these are the kind of things that you have to be careful about with these loops. But you see here, in spite of the fact that the loops get shorter, actually really, as far as complexity, as the worst case scenario is concerned, this is still counts for n times, and this same thing. So the whole thing, if you have a trained eye, and if you've done this many times, you say, okay, n times this, and then each time I have to do n times this, and I have to do this 1 or 2 or 3 times, a fixed amount of times. So this is n times n is n squared complexity, and that is how one very quickly assesses the complexity of an algorithm. And because this one nobody looks at, because it's a constant time that we have to do this, so it's not important. Okay, so number 4. Notice that this was a long calculation, because in the beginning I didn't know what to do, but you could have gone quicker if you said, okay, the summation, this summation, okay, you kind of had to work this out here. You say this is O n squared, and we know from before this is also O n squared, because it's given by a quadratic formula, namely this formula. So O n squared, and this plus 1. Remember, if you have a sum of functions, then the O is the maximum of it. So that would be the maximum of O n squared, and a constant that would be just O n squared. Okay, so right. So let me now do number 4. So I is 1. So this is, okay, procedure, a bit sloppy here. So procedure 4, let's call this procedure 4. And it depends on what does it depend? It doesn't, on a certain n here. Okay, so let me be a little bit here. So I is 1, t is 0. These are just initial initiations, and then we have a while loops, and this is you have to get used to understanding while loops. It's a little bit harder to see there. It's not so obvious direct anymore how many times we count this. Okay, so t is t plus I, and then I is 2I. Okay, so let's analyze this, and then return t, I'm assuming. Oops, return t. Okay, not I we're not interested in. You might ask again, what is this? Well, let's not, I don't want to reveal it yet. I mean, you could try to figure out. How do you figure this out? Well, just take small values for n and see what you get, and then see the pattern. You also will realize what is going on. But let's analyze it just first, complexity-wise. Okay, so these two here, that's just two initial things. So that's two basic steps. It's the while loop. Now, inside the while loop, we do two things. We do two assignments, sum, and remember nowadays we combine all these things, right? We think of this one basic step. Right? You could argue, well, you have to first sum and then declare, and then do a declaration. That's actually 2 steps, but I don't care. And then you could say, okay, you have to multiply with 2. One step. Really, it doesn't matter. Even if I count the whole thing as 1 step, it's still fine, because it's a constant that will not contribute. Now it comes to the question, how many times do I carry out the while loop? Now, naively you would say, I see, n times, right? Because I goes from 1 to n. Does it? Well, let's think. What is I? Well, I starts from 1. You're right. And what is then the next value of I? Well, it's here. It's 2. 2 times 1 is 2. Okay, so 1, then 2. And what is the next value? Oh, it goes from, if I is 2, then the new value of I will be 4. So that will be 2 squared. And then, when I is 4, the next time that I carry out this loop, what is happening then? Well, so let's carry out this program a couple of times, right? So if I is 1, so these are the registers. If I is 1, then the t will become, so before I start, I is 1 and t is 0. Okay. So then the while loop is carried out once. That changes t into t plus I, so t is now 1. And then I change I into 2I, which is now, so I is, so this is I, sorry, this is what I meant to say. So the initiation here puts I equal to 1 and t equal to 0. And so here now starts our loop. So I'll color it a little bit that you see what I mean. So this loop here, this this starts here. Okay, this is the calculation, what happens inside that loop. Okay. I change t to 1 and I is doubled, it becomes 2. Let me get back to my okay, I is 2, so t is 1 and I is 2. Okay, next, what happens then? Okay, I compare 2 with n. Let's say n is some bigger number, so at the moment it still carries it out. So what does it do then? Well, the next step, it's gonna add t and I, so that will be 3. Okay, so this will be 3. And what does it do to I? It doubles it, so I will be 4. Let's suppose that 4 is still less than n, so this we keep going here. So what is happening then? We're gonna add this 4 to 3, right? So this is this step here is adding these two numbers. So that is 7. And then I'm gonna double I, so it becomes 8. So in the next step, you see that, and assuming that the while loop is still going on, we get 15 here. 15, and I double the counter 16. Okay, so what you see here is that the value of t is actually 1 less than I, which itself is a power. So this is the first time I carry this out. So this is the first time I carry 2 to the 1, 2 square, 2 cube, to the 4th. So how many times will this carry this out? Well, as long as 2 to the k is less than n, so it will stop when these are equal. Now, of course, they're never going to really be equal. N is 17, it's never going to be power, right? If they're almost equal, in other words, what I should say is that, so how to analyze this now? So I'm saying, this is k the first time I do this is the second time, this is the third time I do this, the fourth time, and I'm trying to figure out how many times is if I'm going to do this. So what is k, what will the value be k be when I've finished? Because this will be carried out 2k times. Okay, I'm going to carry it out as many times, 1, 2, 3, 4, k1, k2, k3, k4, until the number I get, until this 2 to the k is bigger than n. Until I get in this situation, because that will bring me out of my loop. Okay, so how do we get this 2 to the k is less than, bigger than n, but 2 to the k minus 1 is still before n. That's the previous time I still carried out, it's the next time. So it's the, I'm looking for the k that satisfies this inequalities here, or perhaps equal here, we don't know exactly. How do we find that? Well, you have to take the logs now. So we take log of this side, the log 2, log bit base 2, but I'll just write log, that is k is bigger than the log of n. The inequalities don't change when you take logs, is less than k minus 1. So we can say that k is the ceiling of log of n. Alright, so this is carried out 2 times the ceiling of log of n. Now, the ceiling doesn't change the complexity. And then we have the plus 2 here, so we forgot the plus 2, so I should write this plus 2. So this is the number of steps the program needs to calculate. And so what does this mean now? The O will be, well, as I said, the constant doesn't matter. The ceiling is just one more perhaps than log n, or a little bit more than log n. So again, that will make no difference. So it is just O of log n, which is by we have discussed. We will discuss soon. Is that means a much better, much faster algorithm. And so be careful, right? Just because it looks like it's going to carry it n times, you have to dig. You have to look into the guts of the thing, to the insides, to see how many times it's actually carried out. Now, in a regular for loop, there is no question, because in the regular for loop, for to loop, the counter is the index is always, the counter is always incremented by steps of 1. That's a fixed number of steps. So we always, if it goes from 1 to n, it will be n steps, unless we jump out of it. Now, yeah, so I should perhaps warn you. So I'm going to give this. I know. So this answers the homework problems. But since I remember, I think of this all of a sudden. Suppose you have something that is somewhere in the middle of a program. For I from 1 to n, and then an if statement. Let's do an if statement. This one. If I is bigger than 0, then return I. Look at this program. This is a silly program because think of it, what it's doing. It says, okay, I'm going to loop from 1 to n. So I should put this colon here. And then I'm going to check if I is bigger than 0. The first time it's going to happen, and then it says stop and give me the value of I, which is then 1. So this program is also going to give you 1. And how many times does it work? Well, it looks like there's a loop that it has to do n times, but it doesn't because it only carries out once. The loop is not carried out really. It looks like a loop, but it isn't. So that's why we always have to look inside to see what is going on. Okay? So in other words, what I'm saying, the complexity of this thing is what we call O of 1. It's just, and in this case, it's actually really just one step. It just takes I equals to 1, compares it, so perhaps 2 steps then if you do the comparison, and returns I. So, okay, that just to tell you that you have to be careful when analyzing while and if for loops. And these are the real things where everything matters, right? This is what gives where the complexity comes from using loops. If you have an algorithm that does 7 steps without any loop, well, that's it. The 7 steps are carried out, and that's it. The end of story. Or perhaps even less because there is an if then and then it stops perhaps. So it's only loops, and there are 2 kinds, for and to, and while loops that contribute to complexity. All right.